Assalamu alaikum. I am Sadaf Talha, roll number 080E30. My other group members are Zarmina Amir and Mariam Imtiaz, and we are going to present you the link budget. Basically, there are two objectives for the design of any satellite communication. First is to meet the effective C/N ratio, and second is to carry the maximum revenue at minimum cost. This is the general architecture. The link from the Earth station to satellite is named as uplink and its efficiency is calculated by G/T, and the link from satellite to the Earth station is named as downlink and its efficiency is calculated by EIRP. The C/N is calculated individually for both links, and finally they are added together to get the total C/N. C/N ratio calculation is simplified by the use of link budgets. It is basically a tabular method for evaluating the received power and the noise power. They use decibel units for all quantities so that the powers can be calculated by simple addition and subtraction instead of complex calculations. Link budgets are usually calculated for the worst case, the one in which the link will have the lowest C/N ratio. Following are the factors which contribute to the worst case scenarios. First is, if the Earth station is located at the edge of the satellite covered zone, where the received signal is typically 3 dB lower than in the center of the zone. Also, the maximum path length from the satellite to the Earth station, a low elevation angle, and the maximum rain attenuation also contribute to the worst case scenario.
Now let us find the carry to noise ratio in a satellite link. For this purpose, we need to find two things: the received power and the noise power. Received power can be found by this formula. EIRP is effective isotropic radiated power, GR receiver's gain, LP path loss, LA attenuation losses, LR and LT are receivers and transmitter losses respectively. Now in order to find the noise power, we use a formula KTSPN, where K is the Boltzmann constant, TS is the system temperature, and BS is the bandwidth in which our link is operating. Now let us take a link budget example in C-band downlink for Earth coverage beam. We suppose that the satellite is in the geostationary Earth orbit. For this purpose, we have to consider two cases, for example, in clear air and in the rain. In clear air, we suppose that the transmitted power is about 13 dBW. To avoid intermodulation, we assume an output back off of 2 dB. So in short, the transmitted power is 11 dBW. Now in order to find the transmitter's gain, we use this formula. Over here, 17 is the half-hour beamwidth of the transmitter antenna. Thus, the transmitter gain comes out to be 20 dB and EIRP comes out to be 31 dBW. Now the receiver's gains can be found by the following formula. Over here, eta A is the aperture efficiency while D is the diameter. In our case, diameter is about 9 meter. Thus, the receiver's gains comes out to be 49.7 dB. Now in order to find the path loss, we use the following formula. Over here, R is the distance between the satellite and the Earth station, and in our case it is taken as 40,000 kilometers. Putting the values in this formula, we get a path loss of 196.5 dB. Now there are other losses apart from path loss. For example, the antenna losses due to the worst case, it is 3 dB. The attenuation losses are taken as 0.2 dB, and the miscellaneous losses like antenna mismatch, antenna mispointing, polarization mismatch, and antenna degradation as 0.5 dB. Now the total received power comes out to be minus 119.5 dBW. Now we have to calculate the noise power. For this purpose, we suppose that the system temperature is 75 Kelvin. Our bandwidth is of 27 MHz. Thus the noise comes out to be minus 135.5 dBW. Now taking the ratio of the received power to the noise, we find that C/N ratio is 16 dB. The minimum permitted C/N for this link is 9.5, corresponding to FM threshold of analog satellite TV receivers. Thus, we can say that we have a link margin of about 6.5 dB. This table shows the similar calculations that we have done so far. For example, the transmitter power, the bandwidth, the receiver's gain, the transmitter's gains, the path loss, etc. The received power thus comes out to be minus 119.5 dBW. Similarly, the noise power comes out to be minus 135.5 dBW. Taking the ratio, we find that the C/N ratio is 16 dB.
Now, in the case of heavy rain in slant path can cause up to 1 dB of attenuation at 4 GHz, which reduces the received power by 1 dB. We have already calculated that for the clear air, the value for power received is minus 199.5 dB. By subtracting 1 dB attenuation, we have the new value for power in rain. The system noise power is increased by temperature of 2.3 dB. So we have the new value, that is minus 133.3 dB. The recalculated C/N ratio is 12.7 dB. The minimum permitted overall C by N ratio, as we have already discussed, for this link is 9.5 dB. So the link margin is 3.2 dB. We should always leave a small margin for unexpected losses if we want to guarantee a particular level of reliability. In this case, we will use 2 dB margin link and will examine how remaining 1.2 dB link margin can be traded against other parameters in system. This is the link budget designed for the rain. As we can see that in the previous value calculated for clear air and the attenuation added due to rain, we have the new value of received power at earth station in rain. Similarly, received noise power for clear air was this, and we added increase in noise temperature and we got the new value. So link budgets have simplified the calculations that we don't need to calculate all the values for the rain again. We just added and subtracted the noise and attenuations and we can get the new values. And so there is the C by N ratio in rain, which is 12.7 dB. Now, as we said, we will trade off 1.2 dB of gain for other parameters. We will consider it for diameter of earth station. 1.2 dB value is equal to ratio of 1.32. We know that the gain was 49.7 dB. By subtracting the minus 1.32, we have the new value of gain, that is 48.5 dB. By putting in the formula, we have the diameter, which was 9 meter, is now reduced to 7.8 meter. Similarly, another case, we can change the global beam antenna to regional antenna. Regional beam is 12 dB higher than on excess gain of the global beam. Using the link budgets design, we can trade the extra 12 dB gain of regional antenna for reduction in earth station dimensions. For the example of 9 meter antenna receiving analog FM TV, we can reduce antenna diameter from 4 to 2.25. As antenna gain and diameter have square relation, 12 dB is equal to 15.8 ratio, and by taking the under root, we have a factor of 4. So diameter can be reduced by a factor of 4 from 9 meter to 2.2 meter. These are the references for our presentation. Thank you.